All right, so now let's start talking about the strengths of acids and bases. So I'm going to start off just by saying that strength depends on ionization in water. So strong acids and bases are strong because they 100% ionize. Weak acids and bases do not ionize 100%, so they are weaker than your strong acids. But then within those, some are stronger weak acids than others, depending upon the amount that they can form ions. So let's break this apart. Let's start with a discussion on strong acids and bases. The key feature is that they completely ionize in water. So we use a single arrow to show complete dissociation. We do not write the double arrow for equilibrium because the conjugate partner is extremely weak, right? For example, if you have a strong acid like HA, technically this A minus is its conjugate base, but it's such a weak base that it doesn't have much of a chance chance of accepting that hydrogen ion. So we just say, you know what? Boom, that's the way that we're going to go. Now, you're not expected to have these memorized. There is a list of the 6 common strong acids on the top left-hand side of your relative strengths of Bronsted-Lowry acid and base table. So I'm going to bring up that table, and I'm going to flip my screen so that we can write them down. Okay, here we go. So the 6 strong acids are these ones that are shaded at the top here. These are our 6 strong acids. They include perchloric acid, HI, hydrobromic acid, hydrochloric acid, nitric acid, and sulfuric acid. These are our 6 strong acids which 100% ionize in water. Now, what do we mean by ionize in water? Well, what I want you to notice is that the 6 or all of the acids on this chart are written in their simplified form. So, for example, hydrochloric acid donates a hydrogen. So the simplified form is just HCl forms H plus chlorine ions. And oftentimes that's all you need, right? When we're doing our K calculations at the end of this chapter, I often don't write what's actually happening. I write the simplified form. In Chem 12, you are also expected to know that what's actually happening is the hydrogen chloride gas is dissolving in liquid water to form hydronium ions and chloride ions in solution. So these would both be aqueous. So the relative table only gives you the simplified version, but you're expected to know that these are actually happening in water and that this equation down here is the same-ish as this equation up here. This is just the simplified version. Okay, so then what about our strong bases? Well, if our 6 common strong acids are at the top of the table, then our strong bases are at the bottom of the table. And not only at the bottom, but they switch sides. So the way that this table is laid out is that on the left, you have your name of your acids. And then on the right, they don't give you the name, but these are all of your bases. So your strong bases are your oxide and your amide ions over here. Okay, so those are going to act as are acting as strong bases. The simplified form is that the NH2 minus accepts a hydrogen to form ammonia. And then what's actually happening is in water, the NH2 minus is accepting a proton from the water to form NH3. But here's why it's a base, is that in water, it is producing hydroxide ions. So it's really easy when you look at something like a soluble metal hydroxide, something like a sodium hydroxide, to be like, hey, sodium hydroxide dissociates to sodium and hydroxide in solution. But it's harder to tell for something like an amide ion that it's going to produce hydroxide. because you have to put it in water to see the hydroxide produced. Now, this is something that's going to be important when we get to those equilibrium equations. So the simplified version is totally fine for your acids, but it is really important to understand your reactions with water for your bases, unless you're talking about a soluble metal hydroxide. So just a little bit more about the soluble metal hydroxides. It's any substance which dissociates completely to produce a cation and hydroxide. This is going to include your alkali metals or alkali metal hydroxides and your alkaline metal earth metal hydroxides. So if you don't know what I'm talking about there, let me just rotate my chart. Okay, so when we're looking at these, your green is your alkali metals. So lithium, sodium, potassium, rubidium, cesium, and francium. And we stopped at cesium. But these 5 alkali metal hydroxides are strong bases, as well as your alkaline earth metals. So that's going to be anything written in the blue. And again, we've only written the common ones, which are the calcium, the barium, and the strontium. Awesome. Okay, so that is our discussion on strong acids and bases. Now what we're going to talk about is our weak acids and bases. So the key features are that weak acids and weak bases partially ionize. So they do establish an equilibrium, and we use a double arrow when we write the dissociation of a weak acid and a weak base. So in solution, weak acids and weak bases coexist with their conjugate partners. Now let's focus on weak acids. So weak acids are all the acids except the 6 strong acids. They are found on the left-hand side below the strong acids, but they start at HiO3. So let me just bring up the chart. So we need to get down to page 7. And then flip it back around. Okay, so when we look at this chart, the strong acids are the 6 ones at the top, and then you'd think that the weak acids start here, but they actually start at the iodic acid, and I'll explain that in a bit. But the weak acids are going to go from HiO3 down to the water. Okay, so when we write the dissociation of a weak acid, let's pick hydrofluoric acid as an example. On your sheet, it just says that HF goes to H plus plus fluoride minus. In reality, we know that this reaction is happening in water and forming hydronium and fluoride. But for acids, the simplified version is great, but it is important that you understand this is what's actually happening. Now let's take a second just to talk about the H3O plus. The H3O plus. So again, if you look at this chart, there's this H3O plus that's at the bottom of the strong acids, but it's not, what do you call that? Shaded, right? It's not considered weak. It's actually the strongest acid that can exist in water. So strong acids are all leveled to this hydronium ion in aqueous solutions. And if we wrote hydronium reacting with water, nothing would change. So if you had hydronium acting as an acid with water, then it would donate its proton to the water, which would form hydronium, and then it would form hydrogen or water. So nothing would happen. And if you think about this, we're not there yet, but if you think ahead to the fact that we're going to be talking about KEQ, then you would be dividing something by itself and getting 1. So if you look at this formula sheet, or if you look at this table, right, when we look at the strengths of acids, we're going to be talking about this value of Ka, okay, which is going to be an equilibrium constant. And when we talk about the 6 strong acids, it says very large because they dissociate 100%. So you don't divide by any of the acid that's left, you just get a really big number. Whereas with the hydronium, it was a value of 1. And then everything past there has an actual value of Ka. So all that to say is that when we're talking about weak acids, it's going to be everything not shaded on the left-hand side, except don't include the hydronium ion. Our weak bases are all the bases that aren't strong and not the bases that are the conjugate of the strong acids. So if we look on here, again, if I bring this guy up, when we're talking about the weak bases, we're going to be counting all of the bases on the right-hand side. So we're going to go from water all the way down to, not including hydroxide, but we're going to go down to the phosphate ion because anything with hydroxide is a strong acid. So when we talk about the simplified version, you're just writing the reverse of the um, acid equation. So you're going to go the base plus the hydrogen ion forms the conjugate acid, right? But in reality, what's happening is that the ammonia is accepting the proton from water, forming the ammonium and a hydroxide ion. So now let's talk about that idea of relative strength. So there's strong and then there's weak. And then within weak, there are different acid and base strengths. The rule is the higher an acid is on the acid base chart, the stronger it is. The stronger acids ionize more in solution and they'll have a higher concentration of a hydronium ions at equilibrium. So if we just looked at this chart, and we're going to talk about those Ka values, but I decided to do that later and not complicate this. We're just going to look at in terms of this kind of bar on the left-hand side. These are strong. These are weak. So there's a whole bunch of weak acids, but this is the weakest of the weak. This is the strongest of the weak, and then we've got just strong acids above. So if I asked you which is stronger, you're just looking for which one is higher on the list. So if we look at H2CO3 or SO3, it's here. And then if we look for the HF, it's here. So the one that's higher is the H2CO3. So H2C, sorry, saying C, but I mean S. H2SO3 is a stronger acid. If we wanted to compare H2S and HCN, again, we're just looking for height on the chart. So H2S is down here, and then HCN is down here. So again, the one that's higher is stronger. So the H2S is going to be stronger. Now, if you're wondering why, you can start looking at the right-hand side at the Ka value. You'll notice that the Ka value for H2S is larger than the Ka for the HCN, and that's because there are more ions that dissociate in solution. Okay, so that's the behind the scenes, but all I really need you to be able to do is just look at its height on the chart for now. Then lastly, if we look at base strength, it's the opposite. So the lower a base is on the chart, the stronger the base is. Strong bases ionize more in solution, so have higher concentrations of hydroxide ions. So if I want to determine which of these two is stronger, I'll just split my screen. You're now looking for them on the right-hand side, and the one that's lower is stronger. So with acids, higher is stronger. With bases, lower is stronger. So if we're comparing CO3 2 minus and NO2 minus, you're going CO3 2 minus. Where does it exist as a base? There is CO3 2 minus. And then where's the NO2 minus? Well, the NO2 minus is way up here. So the stronger base is lower. So the CO3 2 minus will be the stronger base. Okay, so then what about SO3 2 minus and HS minus? You can pause the video and give this a go. The hardest part is finding them. So the sulfite ion is on the right-hand side here. The hydrogens, what would that be called? Monohydrogen maybe? HS minus? Anyway, HS minus is down here, so which one is stronger? SO3 2 minus or HS minus? It's the one that's lower on the chart, so the HS minus is going to be stronger. Now, one last thing I think before we finish this lesson is just the relationship between conjugate acids and bases. If the stronger the acid is, the weaker its conjugate base. So as you go up on the left, right? So as you go up in strength of acids, you're going down in strength in base, and then vice versa. So if I asked you which of the following acids has the weakest conjugate base, you are looking for the strongest acid will have the weakest conjugate base. So which of these four acids is the strongest? Well, it's hard when I've got all of these stuff already kind of circled on here. But if you go through and you circle, I can just kind of get rid of all these circles. Okay, so let's quickly circle all of these acids that are listed. So we've got HNO2, and this is good practice of learning where things are because you have to use this chart a lot. So HNO2 is here. Then we've got H3PO4. It's going to be pretty high. H3 because it is triprotic. There it is. And then we've got HIO3, which also should be quite high because it's not amphiprotic, right? It's got that first hydrogen to lose. And then lastly, we've got that acetic acid, so that's CH3COOH down here. And the strongest acid is the iodic acid, which means it's going to have the weakest conjugate base. So the answer is C. Awesome. Go and practice.